YouTube. Okay, yeah, then welcome everyone to our weekly colloquium of the Physics Institute of the UNAM in Cuernavaca. Our guest today is Dr. Tathagata K, and let me say some few words on his vitae. Dr. K is presently working as a de Gapa postdoctoral fellow in the Grupo de Ciencias de Materiales of the Instituto de Ciencias Físicas of the UNAM. And yeah, he joined the ICF in January 2020, soon after completing his postdoctoral stay at the Tel Aviv University in Israel. Dr. K obtained his PhD from the Department of Energy Science and Engineering at the Indian Institute of Technology in Bombay in India in 2018. His doctoral research was focused on the synthesis and electrochemistry of graphene-based materials for fuel cell applications. And his background is electrochemistry of energy-based materials, carbon nanomaterials, and metal oxides, and electrocatalysis. He has keen interest in the design and investigation of electrochemical properties of novel carbonaceous electrode materials for a wide range of energy applications. So, Dr. K, thank you very much for joining us today, and we are looking forward for your talk.
Thank you so much, Dr. Thomas, and thank you very much for this nice introduction and giving me this opportunity to talk in this platform among all of you. And today in this talk, we will be talking about the different carbon-based nanomaterials and their uses for electrochemical energy storage. Overall, in this whole world, this electrochemical energy storage has received a great attention in the recent times because of several factors. And one of them is energy crisis. We'll look into the matters in a little bit deeper way and try to understand the process of electrochemical energy storage. My slides are not moving. Okay. The topics that will be covered today are the different carbon nanomaterials and how do we store charge electrochemically. We'll be having an idea on the supercapacitors, and we will be talking about two different kinds of materials. That is, one is two-dimensional graphene and the role of surface oxides towards energy storage, and a carbon and a three-dimensional carbon and a metal oxide hybrid structure towards energy storage. As I just mentioned, that we are in a midst of severe global energy crisis. Everywhere, I mean, we are using fossil fuels, and the fossil fuels are generating a lot of greenhouse gases, which are not so good for our environment and particularly our health. And so for the last few decades, maybe 20, 30 years, the materials who are working on materials electrochemistry have been working on different materials like this graphene, these oxides of graphene, high surface area materials like the fullerene structure, the carbon nanotubes, and a lot of research has been happening all over the world, both in laboratory and the industrial scale, towards several energy storage devices, which includes batteries and supercapacitors. These batteries and supercapacitors are being used in portable electronic devices like we are using in our mobile phone, laptops, and in hybrid electric vehicles. So in this particular theme, we will be talking about supercapacitors because supercapacitors offers us a very good alternate way to store energy. The supercapacitors are cleaner, they are environmental friendly, and most importantly, the energy storage is sustainable and efficient. Now, what is a supercapacitor? Supercapacitor is nothing but an electrochemical storage device which undergoes the charging and discharging in seconds. So you can charge the supercapacitor in seconds, and you can take out the energy also in seconds, and which is very fast compared to those of batteries, which has the time duration of maybe in minutes or in hours. Supercapacitors usually delivers very high energy density and power density, which is very important for device-based purposes, and most importantly, the stable performance. The stability of a supercapacitor is very important because we need to run it for several thousands of cycles without any degradation of the performance. Let's have a very quick overview of what does a supercapacitor look like. It has two electrodes. One is a positive electrode, another is a negative electrode. And in between, you have a liquid electrolyte. This green area is the liquid electrolyte, which has the positive ions and the negative ions. Now, once this electrode is charged, oppositely charged ions are attracted towards the respective electrodes of having the opposite charge. So this is how the charge storage mechanism is working. And the capacitance, as we can see in this formula, is directly proportional to the area of the electrode and the distance between the two electrodes. I mean, how much distance the electrolyte is covering. So what are the ways of increasing this capacitance? Now, this entire talk is focused on this particular theme. How can we increase the capacitance of a supercapacitor? We can either increase the area, or we can decrease this D. This area can be increased by using a high surface area electrode. What a high surface area electrode, for example, carbon. It's the amount of area which is available for the electrolyte out absorption. We can lower the diffusion length. We can lower this D and by using a porous structure, and also we can incorporate surface reactions or redox-based materials into the carbon to enhance the capacitive behavior of the material. Now, if we look little bit keenly towards what exactly does the high surface area electrode does, we observe that in this micropores of this material, there are innumerable numbers of electrolyte ions which are adsorbed on the surface. This number of electrolyte ions, the more number of electrolyte ions on the surface, the higher will be the charge storage capacity of the material. So in this case, we are looking for a material which is highly porous and having a high surface area. Carbon serves the purpose very well. Carbon is well conducting. The whole world is made up of carbon, and it has very high surface area. We don't need to go too far to fetch a carbon for our purpose. It is near to our hand. And carbon features in several electrochemical devices, in fuel cells, batteries, supercapacitors. For several years, carbon has been serving the purpose of energy conversion and storage, because carbon can act as a support and also as an active material, a support for another material, and it itself can act as an active material. Different kinds of carbon, two-dimensional layered graphene is probably in the past 15-20 years, maybe innumerable number of papers have been published on graphene. But recently, this metal organic framework based porous carbon has came into our hands. In the past maybe 6-7 years, people have started. This metal organic framework is nothing but a structure of a metal and an organic structure. And when we carbonize the structure, it gives a porous and a hollow carbon. This structure, this multi-dimensional structure, has high area, high surface area, and also it is porous. So this is a very good material towards energy storage. As we know, carbon nanotubes, three-dimensional carbon aerogels, and activated carbon, these are well established in the literature towards energy application. In this particular aspect, we will discuss about the electrochemical properties of graphene, and we will talk about the metal organic framework based carbon. Now, how do we synthesize a graphene? What are the chemical ways of synthesizing a graphene? We start with graphite flakes, and we oxidize it and then again reduce it. Let us take a very simple example. Suppose let us consider a book. The book has number of pages. Then we insert cotton balls inside the pages as an oxides, and while reducing, suppose we remove 90% of the cotton balls, and the remaining 10% of the cotton balls are still there inside the structure. So we have a exfoliated graphene oxide structure with all the cotton balls, all the oxide moieties, all the surface functionalities inside the graphene structure and graphene oxide structure. And once we reduce it, we undergo chemical reduction of it. We don't remove the entire oxide groups. We just remove maximum 90% of it, so that the layers remains exfoliated and separated. So this is the whole idea of synthesizing a graphene from graphite. We oxidize it with a strong oxidation condition and put a lot of oxide groups inside the structure and exfoliate it. The graphene oxide is exfoliated. Now we put another chemical to reduce it, to remove the excess of the oxides and to get a structure which has some reminiscent oxygen groups that helps to keep the layers separated and also avoids from restacking. How do they look like? Now, when we take a microscopic image of graphene oxide and graphene, we predominantly observe sheet-like morphology, and the sheet-like structures are folded. It is like a bed sheet in the morning. It is crumpled. So we make our bed to look it properly. So that this look like a crumpled bed sheet. This as an observation, we can observe that this graphene oxide are bigger in size. The sheet size are bigger and have a relatively smooth structure. It is not that crumpled. But when we are reducing this graphene oxide and getting the chemically reduced graphene structure, the surfaces are more crumpled. I hope you can see the crumpled nature of the sheets. It is a transmission electron microscope, and these layers are almost translucent in nature, and we can observe the several foldings at different areas. These foldings are mostly due to the graphene structures are not stable in a straight form. They always want to minimize the surface energy, so they want to fold themselves, and this kind of structures are visible with a chemically defined graphene. Now, to analyze how to analyze the electrochemistry of it. First, we need to prepare an electrode. What is this electrode preparation? Any of this powdered material, maybe it is a graphene or a graphene oxide or any material that we synthesize for our system or for the supercapacitor application, we mix it with a solvent and prepare a fine ink, a fine free-flowing ink. Like this ink, we take in a micropipette and we drop cast on an electrode surface. This is an electrode surface. I have mentioned a glassy carbon electrode, and we can use any other conducting substrate as well. Like people have used nickel foil. Any other material can be used as a conducting substrate for this ink. The best part of this process is that we can analyze the property of the material by taking just some micrograms of it. Some 500 micrograms is sufficient to tell the entire story about how your material is. Is your material good for capacitor, or is your material bad for capacitors? In the next part, what do we do with this electrode? We connect it to a potentiostat and put two other electrodes. Am I muted?
We can hear you. We can hear you.
Okay. Am I audible, right, Thomas?
Sorry, I didn't get it.
I'm audible, right?
Yes.
Yes. I actually, it was showing that I'm muted. So
yeah, for one
Sorry,
second,
I was trying to accept someone.
It's fine. It's fine.
Okay.
So what we do a very simple thing. We put this working electrode in an electrolyte. We put another counter electrode and we put a reference electrode. Now, what is this counter and reference? So in a system, to have a continuous flow of electrons, you need a positive end and a negative end. This working electrode would sometimes act as a positive end, and the opposite charge is there on the counter electrode. That means this cell is filled with an electrolyte. So the working electrode and the connection between working electrode and the counter electrode is done by the electrolyte. The electrons do flow out of the counter electrode and flow into the counter electrode, thus thereby balancing the charge of the working electrode. With this reference electrode, we can accurately control the potential of the working electrode, and all these three electrodes are connected to a potentiostat. What kind of measurements can we do? there are usually two kinds of electrochemical measurements that are being performed to identify how good a capacitor material is. The first one is cyclic voltammetry. The second one is galvanostatic charge discharge. Let us little bit go detail what are all these things. What is a cyclic voltammetry? Now this figure is a current versus potential graph. We take this is a typical voltammogram of a graphene based materials. This is our working electrode. What we do, we run this potential from here, from the lower end, and go to the higher end potential. This is called anodic scan, and we come back to the starting point. This is called the cathodic scan. This entire anodic and the cathodic scan generates a loop, a cycle, and this cycle can be repeated several times to get the cyclic voltammograms of a material. So most interestingly, we can calculate what is the specific capacitance, or how good this material is for capacitive applications. This one, with this formula, we can calculate this area of we can calculate the capacitance from the area, from the mass of the active electrode material, the scan rate. The scan rate is the velocity of at what rate did you scan it can be done at 5 millivolt per second, it can be done at 20 millivolt per second, and based on this and on the potential window. What is this potential window? The difference between the starting potential and the final potential is the potential window. So from this equation, we can calculate the specific capacitance of any material. Since this is directly proportional to the area of the absolute area of this loop, higher the area of the loop, the better is the capacitance. So that is what we see. We will be seeing in the following slides. The better the current, the better you get the current at a particular potential, the higher is the capacitance of your material. We can also calculate the capacitance of the material from galvanostatic charge discharge plots. Galvanostatic, at a constant current, we charge an electrode up to a particular potential, and then at the same constant current we discharge it. What we measure in this plot is this time. This time is very important, because when we want to calculate the capacitance from a charge discharge plot, this is directly proportional to the time of discharge. So higher the discharge time, the more time your electrode is taking to discharge, the better your capacitor is. The better the capacitance of the material is more better. Now, putting this the whole idea of cyclic voltammogram, how can this cyclic voltammetry or the cyclic voltammograms can be used to determine the electrochemical properties of an oxide-based material? We can do a cyclic voltammetry study of the graphene oxide. Not to get confused with the complex figures, I will try to explain it in a little bit more easier way. So this entire up one, the figure A, is is showing the electrochemical properties of graphene oxide, of a graphene oxide electrode. This is a graphene oxide electrode. Now, when we take the electrode from a higher potential to a lower negative potential, the negativity, the charge of the electrode is more negative. When a charge of the electrode is more negative, it tends to reduce the oxides of the electrode. So this is we see, and we do about 60 cycles to get the complete reduction. Initially, this is the initial cycles. We see a high reduction current, because at this time the content of the oxide is more. But what happens with time? Every time I am going at -1.2 each time the current is observed to decrease. This is because at every cycle a part of the oxide is getting removed from the system. So slowly this graphene oxide is getting reduced to graphene. or we can say a reduced graphene oxide. This is an electrochemical process. Now, if we go a little bit deeper into the voltammogram, we observe that in parallel to this reduction process happening here, we can observe that there is an increase in the double layer current. This increase in the double layer current is mostly because of the conversion of this graphene oxide electrode to graphene. This graphene has also, we can see this redox peaks are generated in the system. Graphene has some some functional groups which are electroactive in nature and contributes to the capacitance of the system. So with cycling, we are able to generate this kind of electrochemically active functional groups which can contribute to increasing the capacitance of the material. And as we can observe here, the structure of the electrochemical reduced graphene is also the same. It has also highly crumpled morphology and folded structure. It is one of the indication that the graphene, the structure is devoid of its oxygen moieties. Now, we achieve this kind of reduction in an electrochemical condition. Is this possible? Is it somehow possible to have an external factor? Does an external factor help us to generate this functional group? Can we enhance the capacitance quite easily without the thing? Yes, it is possible from the thermal reduction of the graphene oxide. The thermal reduction, what happens? We put a graphene or a graphite oxide or a graphene oxide and subject it to heat treatment at different temperatures at 120, 150, 200, and 300 degrees centigrade. During this heat treatment, the water content and the oxide content of the graphene oxide is removed in the form of carbon monoxide and carbon dioxide. So we are able to reduce the system externally by applying heat. So based on the temperature, what we observe, the extent of oxide reduction varies, which is evident from the recorded voltammograms that will be showing here. At 120 degrees centigrade, we do not observe any reduction of the graphene oxide. Yeah, because when we put this 120 degree treated sample on the electrode, it shows the same properties of a normal graphene oxide. That means 120 degrees centigrade is not sufficient to reduce the graphene oxide thermally. What happens if we slightly increase the temperature to 150 degree maybe? Yeah, partial reduction is we can observe. The number of cycles here is more and the number of cycles here is less. This is because the electrode is taking less number of cycles to get reduced, because the material has already been reduced thermally at 150 degrees centigrade. The interesting thing happens at 200 degrees. Just if we increase 50 degrees centigrade, we observe a complete reduction of graphene oxide to graphene, to thermally reduced graphene. We don't see any kind of reduction curves. Here we see the current is very high, but here the current is low. The voltammogram gets the properties very fast. It has already these are the primary cycles. It has already the redox functional groups, and the structure is already a graphene at 200 degrees centigrade. But if we further increase the temperature to, for example, to 800 degrees centigrade, so as I told that you have inserted cotton balls inside the pages of a book to separate it. Now you are removing it at 800 degrees centigrade. I have removed almost all the cotton balls from the pages, and the pages will now tend to stack. So this is called what is called thermal graphitization. When you have removed maximum amount of oxygen content and the layers are very near to each other, almost graphitized, at higher temperature, this is very highly possible, and we get a very low poor capacitance. Almost the capacitance has fallen down by almost 1 order of magnitude. It has fallen. So what we conclude is that we have to restrict ourselves to graphene by preparing the graphene by thermally reducing the graphene at 200 degrees centigrade, and beyond that, it will start to graphitize and it won't serve our purpose. We get the maximum capacitance at 200 degrees centigrade. So from this part of this talk, what are the major takeaways? We understand that cyclic voltammetry is a very important tool towards electrochemical characteristics. It is the fundamental tool. We prepare any material in our laboratory, we first record one cyclic voltammogram to check whether this material is fine or not. Then the surface functionalities of graphene oxide, yes, it can be electrochemically reduced, generating an electrochemically reduced graphene. The presence of active functional groups is perhaps it leads to the enhancement in capacitance. In short, the conversion of graphene leads to the generation of active functional groups, which further enhances the capacitance. Slowly we see a rise in the current. This rise in the current is due to the formation of graphene. And thermal treatment is a very easy and effective way to reduce graphene oxide. We don't need complex mechanisms. We prepare a bulk graphene oxide and we just put for 15 minutes at 200 degrees centigrade. Yes, and we get a lot of graphene. This is very easy way. It's one of the, and we don't need toxic chemicals or anything else. Just a 15 minutes treatment at 200 degrees centigrade. How much ever graphene is required, we can just generate it. Now, what we observed that this redox and the pseudo capacitive materials are very important for capacitive enhancement of the carbon nanostructure. What happens if we just include some metal oxides? What are these metal oxides? This is the second part of this presentation, that we will be talking about different metal oxide and carbon composites for supercapacitor application. So essentially, a carbon and a metal oxide surface has all these properties. It has an active support of the carbon. The carbon substrate is conducting in nature. The carbon has some core elements. Suppose, for example, if we functionalize the carbon, it will behave in a much better manner. But this part is not a part of we haven't worked on this area till now. But at the same time, we have put this transition metal carbon has two different kinds of bonding. One is a physical bond, that it is just like sand on a piece of paper, and the other one is like chemical bond, where there is a true chemical bonding between the metal oxide and the carbon. And the carbon can be doped with heteroatoms like nitrogen and several other sulfur and any other materials. It can be doped. What is the exact role of these spacers of this metal oxide? The metal oxide has a very important role. It acts, not only does it gives the capacitive behavior to the hybrid, the pseudo capacitive behavior to the hybrid, but it also acts as spacers. The spacers the metal oxide particles goes inside the carbon structure, and it avoids the restacking of the carbon, and it allows in the process better entry of the electrolyte ions to the electrode material. This is very important. When we have more, as we have seen earlier, the entry of the electrolyte ions is very important to the structure. If the surface area is not ready if the electrolyte ions don't have a proper access, then our capacitance will decrease. So as a part of this thing, we can say that the charge mechanism in a composite is mostly is based on the capacitance of the carbon-based structure and pseudo capacitance coming from the metal oxide structure. Now I will little bit explain that what is exactly a pseudo capacitance. A pseudo capacitance is kind of a Faraday reaction happening. Faraday reaction means there is a direct transfer of the electrons. When there is a direct transfer of electrons to the electrode material, or there is a electron exchange with the electrolyte and the substrate, the current increases. So that is the role of this metal oxide. It gives a pseudo capacitive enhancement in the current. Among the several metal oxides which are reported in like this manganese oxide has been reported heavily. The ruthenium oxide is one of the first transition metal oxides that has been reported. Cobalt oxide, nickel oxides have been studied. But cerium oxide, what we found in the literature, the studies on the cerium oxide is relatively rare. Why did we choose cerium oxide for this work? Because cerium oxide is one of the most abundant metal oxide. We go for materials which are very easy for us to access, and it is a cost-effective material, and it is very easy to tune its nanostructure. The structure of cerium oxide can be finely tuned, and because of its heavy pseudo-capacitive properties. In this plot, what we see is that this blue curve, these are all cyclic voltammograms. This blue curve is of cerium oxide, and this red curve is of a graphene. Both are having independently low capacitance, but when we prepare a hybrid out of it, cerium oxide and graphene and reduced graphene, the capacitance increases, the current increases. So this is the whole idea of preparing using cerium oxide because of its decent pseudo-capacitive properties. Now, I would like to focus on a part of this thing that we have synthesized quantum dots of cerium oxide. What is the need of these quantum dots? And what are these quantum dots? Quantum dots are having the particle size of 3 to 5 nanometers, extremely small. And a uniform dispersion is possible on the carbon substrate. The quantum dots also provides very short diffusion length for ion transfer. Rapidly, all the electrolyte ions can just, because of this small structure, can just access to the sites very fast. This enhances the pseudo-capacitive properties of the material. Now, our metal oxide is sorted. What we do to have the proper carbon substrate? What kind of carbon substrate did we choose? We have chosen a metal organic framework derived carbon. Now, what is the metal organic derived framework carbon? It is a chemical structure of metal and an organic structure. It is a three-dimensional structure. As we can see in this image, it is a polyhedral structure with multiple sides. These multiple sides offer a high surface area, almost more than 1,000 meters square per gram surface area. A metal organic framework based carbon can deliver. It has highly porous structure. This porosity is not observable from here, but we can do other experiments to determine the porosity of the material. And it is a very highly conducting, and it has a easy synthesis process. Now we get to a recent work from our laboratory group of the Ciencias de Materiales in Instituto de Ciencias Físicas. We have observed some very unique properties, very unique features from our synthesized metal oxide and a carbon composite. Let's start from the beginning. How we synthesized a ZIF-8 structure. By using zinc acetate and methyl imidazole, we synthesized a ZIF-8 structure. This is an example of a metal organic framework. What we did a very interesting step. We used an acid called a tannic acid, and we just etched out the internal matter from the ZIF. Like, for example, if you have a box full of books, you take the books out, keeping the box empty. This is kind of an empty box structure. Now, this even if we have an empty box, if the empty box is not conducting, it won't serve our purpose. We need to have a conducting substrate. So we carbonized it and did the HCl etching to have a very good porous structure of the material. And this carbonization step is essential because it improves the conductivity, and this HCl etching induces a lot of porosity in the material. Because this etching etches out the zinc content. The zinc content is removed with this HCl etching. Therefore, the positions of the zinc metal is now vacant, and it acts as a pore. Now, in the final step, we have put in cerium oxide particles, and like a well decorated, like gold particles on a black on a black carbon sheet, we have gold particles. It looks the structure is something like this. What is the real state of the structures? Yes, these are the ZIF-8 particles, which are solid in nature. These are the actual particles which we have seen in the microscope. We add the tannic acid, it forms the hollow structure, and then we carbonize it. The hollow structure is remained, but without any change in the structure. The entire stuff is hollow. We put in cerium oxide, but from this same images, the cerium oxide are not visible. How can we analyze it? We did a dispersive spectrum, electron EDS spectrum, to check the presence of materials in this system. So we have carbon, we have oxygen, we have nitrogen, and also most importantly, we have cerium. So we could identify that yes, our material has the cerium and the oxide content. Are these cerium oxide physically observable? Yes, they are. The presence of the cerium oxides can be observed from a transmission electron microscope images. We can see, as marked with these red dots, these are the small cerium oxide particles in the system. And the cerium, when we did a size distribution analysis of the cerium oxide quantum dots, we observed that mostly the sizes are range of 3 to 5, 3 plus minus 1, around 4 nanometer size. So therefore, we can not all nanoparticles we can term as quantum dots. Only the nanoparticle size which are less than 5 nanometers can be termed as the quantum dots. Therefore, the cerium oxide particles can be termed as quantum dots. Now we do the most important part. We try to study the electrochemical properties of these materials. Please don't get confused with these too many lines. These are all the cyclic voltammograms of different materials, different cerium oxide. At the final stage, what we did, this cerium oxide as deposited, as synthesized, doesn't work that good. What we need to heat treat it. So we did an heat treatment at different temperatures, and we observed that the cerium oxide quantum dots dispersed on the hollow carbon, which are synthesized at 250 degrees centigrade, this green cyclic voltammogram gives us the maximum capacitance. And at the same time, in this charge discharge plot, as you can show on the right hand side, this shows a maximum discharge time. So this material has a better in comparison with the other materials, it has a better charge storage properties. So I mean, as is demand from the scientific world, that we need to analyze any material in a device perspective. That what happens if you put your material in a real device, how will it function? You need to analyze the material in a device perspective. So we try to analyze this hybrid, this 250 material in a device, in a symmetric configuration of the device. Now, what is a symmetric configuration? Both the positive electrode and the negative electrode are made of the same material. So what we did, we took two conducting substrates, we took two graphite plates, and we drop cast the same same material of this 200 hybrid and fabricated the device. This device showed a very good performance at the different potential windows we checked. As I mentioned earlier, to have a good device performance, we need to have a good energy density. The energy density is given by the formula half the CSP of the material, the capacitance of the material, and it is proportional to V square. V square is the potential window. So this material, we need to check to what potential window it can work the best. We started from 0.8, we went to 0.9, we went to 1, we went to 1.1, and nothing happened up to 1.2. See, I would like to mention the role of the electrolyte here. The electrolyte plays a huge role. Usually, oxygen starts evoluting. There is an oxygen evolution from the electrode if we go beyond 1.2 volt. So the good part is our material just touched that point, that evolution point, but still there is no evolution of any oxygen from the surface. We don't get any high current here. So our electrode is stable. So further, the stability is analyzed from these voltammograms, which are recorded at different scan rates up to 1.2 volt. We observed that even if we increase the scan rates, the shape of the voltammogram doesn't change much. It remains the quasi-rectangular. It retains the quasi-rectangular behavior. The heavy. This is because the cerium oxide quantum dots decorated porous hollow carbon is a very good material for capacitive applications. We have received some really interesting results with this, and this material also gives a very high energy density at a high comparatively high energy density and power density compared to other materials of the same genre. Now this question comes: why did this particular material showed a better capacitance? The reason that we found out was the presence of oxygen vacancies in the system. The oxygen vacancies in this hybrid was determined from 3 analyses: the HRTM analysis, the electron paramagnetic spectrum analysis, and the Raman from the Raman spectrum. This material, from if we keenly look into the structure of the lattice structure of the cerium oxide quantum dots, we will find a lattice breakage. In the literature, it is reported that if there is a sudden lattice breakage in the lattice structure of the cerium oxide, it indicates the presence of a oxygen vacancy. This is confirmed from the EPRs, from the electron paramagnetic results, where we get a strong signal of at the G factor of 2, which is equal to that of a free electron signal in the spectrum. And also we did a Raman spectrum of the material, in which this peak at 598 degrees, we have rechecked with the literature that if we get a strong signal from cerium oxide at this particular wave number, it indicates the presence of oxygen vacancies. Now, what do we learn from this section? We learned that the oxygen vacancies in metal oxide is very important because it improves the electronic conductivity by facilitating the cerium +3 and the +4 state. So the cerium oxide has 2 different oxidation states, the +3 and +4. These oxygen vacancies, if it is there, the interconversion of cerium +3 to +4 and back to +3 is very easy. This is easy. The easy interconversion can lead to a high pseudo capacitance of the material. The quantum dots, the fine quantum dot particle size decreases the diffusion length of the electrolyte ion to a great extent, and thereby enhancing the capacitance. And definitely the porous hollow carbon substrate, what we have used in the structure as for our material, it acts as a good conductor and has a very good support for the quantum dots. So I would like to share that this is the recent article that got published on this current work in Journal of Colloids and Interface Science. And I would like to conclude this presentation with the points that high surface area conductivity and the pseudo capacitive nature of the material is highly essential to make a material a suitable material for supercapacitor. And the metal organic framework derived carbons can be a promising substrate for energy applications. And we are currently working on designing aerosols with metal organic framework derived carbons to build robust supercapacitor device, we have this kind of stable structures of aerosols, and we are trying to devise a material and devise a supercapacitor to design a supercapacitor device. And we are trying also in our laboratory at ICF, we are trying to build a small prototype supercapacitor device. And the current work in progress, our first idea is to maybe to light a small LED bulb with the kind of materials that we are working on. And capacitive desalination is a very good area that has been working on. People have been working on capacitive desalination, that they use this high surface area material to desalinate the water, to remove the salt content from the water. And we are also looking forward to design novel materials for photocapacitor application. Photocapacitor is a capacitor which is photoactive and can work under the sunlight. This is perhaps one of the most important slide. Our deepest gratitude to Dr. Herein for supporting us in every aspect of our research here at ICF. Our group, the material science group, and sincere thanks to Dr. Lorenzo Martinez Gomez, who is no more with us, and sincere thanks to Dr. Mohan, Dr. Socorro, Dr. Maura Casales, Jose Juan, everybody, and they have all have been working hard to make this research successful. All the students, Esperanza, Carla, Daniel, Ceci, Rene, I like to thank all of them. With all the discussions having with them, it helps us to improve our own understanding of the materials. Our professors at IIT Bombay, Professor Manoj Juligat, Professor Shankara, Professor Bala Subramaniam, our collaborators in Mexico, Dr. Srinivas from Universidad Juárez Autónoma de Tabasco, Dr. Norberto Hernandez, como in IPM Mexico, and most importantly, we would like to Material Science Group is highly acknowledges the contribution from our international collaborators, Dr. Shidolu from National Institute of Material Science, Japan, Professor Yusuke Yamauchi from University of Queensland, Australia, and Dr. Sheikh Kadir Pasha from VIT University in India. And the postdoctoral scholarship from Digapa UNAM is also acknowledged, the candidate grant from SNI, and the funds for research received from Cornasys Center, and the PAPIT project from Digapa UNAM, Mexico. I would like to thank you for your kind attention and your patience. Thank you very much, everyone.
Yeah, thank you, Tathagata, for this wonderful talk. So very nice talk and very impressive work. So I enjoyed it very much. And
thank you, Dr.
My congratulations for this work. And yeah, are there comments, questions from the audience?
Please.
Then I may start with one question. So you started your talk showing graphene and graphene oxide as an electrode material.
Yes.
So how is the structure of the graphene? Have you just a single layer of graphene, or are these bilayers, tri-layers?
Yeah, I did one time, Dr. Stegman, I meant to this graphene is difficult experimentally to derive a monolayer of graphene that we usually know. So what I did with I did a atomic force microscopy experiment one time. It is usually 2 to 3 layered. It is not a monolayered graphene. It is a 2 to 3 layered graphene, can be considered a very thin layer of graphene in this area of electrochemistry. It is not a monolayer, as you have mentioned. It is monolayer is not stable. First of all, we won't get any signal from a monolayer graphene.
Okay, okay. And as far as I understand, a single monolayer of graphene would neither be a good electrode material, because you showed later that this nanoporous carbon is much better, right?
Yes.
So
because of this singularity of this layer, what would happen that if you put this into an electrolyte, the substrate will dominate the current from the graphene. So you won't get anything from graphene.
I see. Then later you showed these results from cerium oxide, and then you showed that the combination of cerium oxide with graphene was much better.
Yeah.
Yes. What is the structure? I did not get completely. What is the structure of this cerium oxide plus graphene? Do you mean the structure which you discussed later? Later you showed this nanoporous carbon.
Metal organic framework derived. It is a 3-dimensional structure, Thomas. So it is like a box.
So, I understand. I understood this and you're referring with, when you mentioned cerium oxide plus graphene, you were referring to this structure which you discussed later.
Yeah.
Okay.
So this graphene, cerium oxide graphene will be no. I have taken the data from the literature. That it is a different work altogether, Thomas. The cerium oxide graphene is not. So we haven't worked on the cerium oxide graphene. We look forward to it. Will give us a very good information regarding electrochemistry. But what we use is not graphene. We used a different carbon structure, and we saw that the same property that happened with graphene, that it increased the capacitance of the material. We also saw that when we put on a porous hollow carbon structure, because I would like to show you the result. So this is the result, Thomas. This is a porous hollow carbon without cerium oxide. Once you put the cerium oxide, we get almost 3 times improvement in the capacitance. This is our result, actually.
I see. Very impressive. Very impressive. Yeah, thank you very much so far. There is a question from Dr. Naveen in the chat. I will read the question. So, good scientific talk. First question. As you mentioned about carbon and high surface area materials, does nanographene or graphene quantum dots composites can help in capacitance boosting?
Yes, of course. Several research is going on currently on working on graphene quantum dots, but what I think is we need to take care of the loading of how much graphene quantum dots you are putting onto the surface to get a decent response from the materials. So this has to be checked, but definitely for sure, graphene quantum dots and other carbon quantum dots can be used for boosting the capacitance of. For sure, it will work.
Okay. And the second question is a general question. What is the reason behind on fires, probes, recalls the electric vehicles?
I didn't understand much of this question, Thomas.
Me neither. So, Dr. Naveen, can you explain your second question a bit more? I don't understand. So maybe is there another question from the audience, another comment?
I have a comment or other question.
Okay, go ahead, Thomas.
You looked for a very specific material to add in, and you emphasized that this was chosen because it was easily available, non-contaminating, and all the sort of nice properties. Can you somehow characterize the family of materials which, or of substances to include, which may do the trick, but which maybe are toxic or maybe are expensive or maybe other things, but just some idea? I mean, is it common to have that effect, or are there very few materials that may have that effect?
Yes, yes, Thomas. Thank you for this question. There are wide range of oxides available in our nature. Not all the oxides do behave in the same manner. So, for example, manganese oxide, some reports are there where manganese oxide is behaving as a good capacitive material, and in some paper they haven't shown it in a better way. So as you have said, that we need to characterize any oxide, new oxide we take, whether this oxide will be helping the entire idea of enhancing the capacitance. We need to be very selective. We need to do not only the physical characterization, we need to do the electrochemical characterization, prepare stable electrodes with this material, and we can analyze the charge storage properties. Yes, we can do that, Thomas.
But you have no way, to say, okay, maybe this group seems attractive, this other group is a bad idea. I mean, I guess there are some rare earths which are so expensive that you don't even want to think about them. So price is obviously a conjecture, but in principle, you look at any oxide.
Yeah, so but that is what I was trying to explain, Thomas, that any oxide does not show
I know, but is there a general principle that that you could say, oh no, this kind of oxide, independent was it's cheap and easily available and all that, it won't work because of some reason. So it's only this family of oxides we can consider. Or do you really have to calculate and test everyone individually, except if it's already much too expensive or too toxic at the beginning?
For example, the family of transition metal oxides, Thomas, has been, can for sure say all the materials from this transition metal series in our periodic table, they can be used as a capacitor material.
Oh, good. Thank you very much. And also, thank you for an excellent talk.
Thank you so much, Thomas. Thank you very much for your comments.
There is a comment from Mohan. Mohan, you raised your hand.
Yes. Thank you, Thomas. Thank you, Carl, for your. I have a kind of a question. You are let us be in the same slide, right? So you are telling your carbon is porous. And now you are trying to immobilize the cerium oxide quantum dots on it. Okay.
Yeah.
So did you try to check the pore size and the quantum dot size? So why? Because if you load your pores with the quantum dots, the surface area obviously decreases. So area decreases.
Yeah.
Access of ions into the surface or onto the surface differs. Did you ever study this particular phenomena, whether or you need to optimize how much quantum dots I am supposed to immobilize onto the surface? Is there any strategy to control these parameters? If you overload, for sure, your pores will get blocked.
Yes. There should be Dr. Mohan regarding how much quantum dots. That is how, while preparing the untreated quantum dots, we need to be very sure what is the mass ratio of cerium oxide that can be formed, and the mass ratio of the carbon that we are taking. So yes, the pore sizes are very important for us to understand, because if as you have said, if the pore sizes are the same, or there is a tendency to block the pores can get blocked. But what I believe that these quantum dots will have a natural tendency to go and sit on the surface that is available outwards. Not the access to the pores will be a secondary phenomenon. But this is a matter of research, Dr. Mohan. We need to work on it. It's a very good question, and but I feel that before going inside the pores, the carbon, the structure which is available, the cerium oxide go and sit there, and some pores can be blocked, and but that would be negligible, I believe, in the greater scale. And once you put a lot of all this cerium oxide quantum dot, it will overall there will be an enhancement in the capacitance under any circumstances.
Well.
Okay. Thank you very much.
Thank you.
You wanted to add something, Mohan, or?
Yeah, that's it, Thomas. Actually,
Okay.
I have one general question. He's just Dr. Carr. You were mentioning here CeO2 minus S, no? So representing an oxygen vacancy in cerium. So what happens if you are decorating a pristine cerium oxide quantum dots? Is it possible to control a pristine cerium quantum dot into the level of quantum dot? What happened to the surface states if you reduce the size? Is it possible to control it as a pristine CeO2? And if it happens, what will be the response?
I mean, you are telling that to further reduce the sizes of the quantum dots, or to
No. Instead of having an oxygen vacancy, is it possible to reduce the size of cerium oxide into the level of quantum dot without any surface defects? Is it possible? If it is possible, how will be its how will be the capacitance performance?
no, that means you are telling that the quantum dots, the sizes will suppose 1 to 2 nanometers, like one.
Yes, without any oxygen vacancy, a pristine cerium oxide can be decorated on a
yes, it can be decorated. Yeah.
In that particular case, how the capacitance may change.
Yeah.
So here you are illustrating that this is because of oxygen vacancies.
Yeah.
But well, the question goes, no, without oxygen vacancies, can we able to see the same phenomenon?
Yes, right. So if we have a higher particle size of the cerium oxide, more pristine, I believe that the capacitance will decrease, Dr. Mohan. There will be a decay in the that is the reason we need to shorten we need to lower down the size of these nanoparticles in a if we want to use a pristine cerium oxide, we have to have a smaller size for sure. Higher size of the cerium oxide won't give that much capacitance, I believe.
Thank you.
Okay, thank you very much. Are there further comments, questions from the audience?
Sí, yo, Maura Casales.
Sí, doctora, por favor.
Car, ¿me puedes explicar, por favor, las ventajas de usar estos materiales por su gran almacenamiento de carga en comparación con las baterías?
¿Cuál, doc? ¿En el grafeno?
Sí.
Okay. En este la ventana es 0.8 voltaje, doctora.
Ok. ¿Y qué ventajas al usar estos materiales tenemos en cuanto a contaminación con referente a baterías, a celdas de almacenamiento? ¿Tú qué me puedes decir al usar estos materiales de grafeno?
Sí, doc, por las baterías yo creo podemos usar una ventana más grande, más de 1 voltaje, doctora.
Sí. ¿Tú podrías construir un prototipo con este tipo de materiales a futuro?
Sí, claro que sí, doctora. Podemos hacer una dispositivo con estos tipos de materiales y podemos hacer podemos aprender una luz en nuestro laboratorio.
Ok. Ahora bien, yo veo que, ¿qué área de tu electrodo estás usando y qué espesor aplicas a este electrodo?
No entendí bien, doc. Por favor, otra vez.
El área del electrodo, el diámetro, ¿cuál es? ¿Y cuánto aplicas de película?
En toda la área de electrodo, Doc. Es bien, nosotros ponemos la gota en la electrodo que cubre bien. No hay espacio para, no podemos dejar espacio para los iones de electrolito pasar adentro de la sustrato. Queremos cubrir todo la electrodo con la tinta de material. Todo es 0.196 centímetros cuadrados, doctora, esta área.
Ok, a eso me refería. Que es muy poquito material.
Es muy poquito material.
Y la respuesta en la voltometría es muy alta la capacitancia.
Sí,
o sea,
sí.
Quiere
es
decir
más
que
mejor.
el material es muy eficiente y da muy
Sí.
buenas respuestas.
Sí, porque la ecuación dice, Doc, tú puedes ver la M, cuando nosotros ponemos muy poquito cantidad de este tipo de material sobre la electrodo, sale más grande, más bien la capacitancia, porque este es un denominador. Es más poco, es más mejor, es más bien la respuesta de la electrodo.
Sí.
Por eso usamos este tipo de material como una carbón de vidrio, cual sirve muy bien para nuestras pruebas.
Sí, es a lo que yo me refiero. Lo que pasa que yo veo una pila,
sí.
Una pila normal es muy grande.
Sí.
Y es más material que el que tú estás aplicando.
Sí.
Okay.
Podemos preparar muy pequeñas celdas, cual sirve mucho mejor que los pilas, otro tipo de pilas, cual es más grande, usa más materiales. Podemos usar muy poco de materiales con este tipo de electrodos, Doc.
Ok, muchas
Pero
gracias,
este tipo
doctor.
de electrodo, esto es caro, pero podemos usar en el futuro, decíamos, podemos usar en el futuro. Gracias, doctora, por su
Muchas
pregunta.
gracias, doctor Carr, y felicidades por tu español también.
Sí, muchas gracias. Yo entiendo, al menos, Doc. Muchas gracias a ti para todo su apoyo, Doc, para todas las cosas.
Okay, muy bien. I will switch back to English.
Yeah.
Are there further comments, questions from the audience? So Dr. Naveen specified a bit more his question.
Yes.
So he is asking on these problems with these batteries in cars that, well, you have to store a lot of energy in these systems, and they can catch fire and can be damaged. So I think his question goes a bit in the direction of the question of Maura.
Yeah, probably because of the leakage currents, Naveen, what I think. I mean, all these batteries do have, suppose if we keep a battery for a long time in our house, it starts leaking. And this is maybe due to the improper fabrication and to the internal reactions happening in the battery. So what we can, yes, you are true that all these companies are recalling electrical vehicles, and due to and we can use some kind of non-corrosive materials which will not catch fire. Maybe we have to find out this kind of materials in future that can help us. Yes, I mean, if this kind of problems arise, we have to find solutions in the areas that we can use materials that are not susceptible to catch fire. We have, suppose, for example, if we use a photocapacitor, for example, and we put a kind of a shed in above the car, it can generate the vehicle. I mean, we don't use batteries. We use something else. We use an energy conversion device, not a storage maybe. So it will just directly get the sunlight, have a maybe small storage part to be used for the night times, but it can using solar instead of batteries can be another option. I mean, I feel so. we'll discuss about it. I mean, thank you for this question.
Okay, thank you very much. Are there further comments, questions from the audience? Yeah, if this, I may add one last question.
Please, por favor, Thomas.
Regarding these two questions from Maura and from Naveen. So in your talk, you presented these prototype devices as supercapacitors.
Yes.
Right. And now the people are asking here for batteries. As far as I, as a non-expert, understands, batteries and capacitors are different devices. So can you construct a battery from using these electrode materials?
Yeah, actually, Dr. Thomas, there is not much difference in the materials actually. So the materials that are being used for batteries, they're somehow fine-tuning the materials to be used for supercapacitors. There is not much, technically there is not much difference. What the supercapacitors we are trying to use is that, I mean, we don't have, we want to have a fast discharge in seconds, for example. It don't discharge that long like that of a battery. So maybe controlling the shape, controlling the morphology of the material can help in this. For example, I would like to, lithium-ion batteries uses lot of graphene. I mean, in the lab I was working at IIT Bombay, our neighboring lab, they were preparing kilograms of graphene in front of me. So, what they used to do, they would insert these lithium ions inside the graphene structure, and this insertion and deinsertion is the entire electrochemistry of lithium-ion batteries. So, basically, the materials are the same. Just we are playing around with the structure, with the morphology. We're putting this material and mixing with another material and trying to get results which can be segregated. Okay, this is a supercapacitor. This material is a battery. So this is the entire idea. Ultimately, your question is very good. It is the same stuff overall. It's nothing much different about it.
I see. Okay, thank you very much for clarifying this. And yeah, thank you again for this wonderful talk and this very interesting results. Again, my congratulations. And
so much,
yeah, if there are no other questions, yeah, thank you all and see you next week. Bye-bye.